Okay, shall I just start?
Your host is, who is your host?
No, I'll take any host. I just
Well, I hope, yeah. Well, thank you, everybody. Good afternoon. I'm very pleased to introduce you Professor Susha Parameswaran from University of Liverpool, who's talking to us about dark energy and its possible friends.
Thank you. Thank you very much for the invitation. It's really lovely to be here. So indeed, I've given this rather Liverpool inspired title to the talk, that energy with little help from its friends, and why it might meet somebody. So hopefully the title will become, the meaning of the title will become clearer as the talk goes on. I'll be talking about various collaborations. Let me highlight in particular my two excellent students in Liverpool, Joaquin Gomez and Bruno Bento, who is actually now in Madrid on a postdoc, and I have several old friends there. Okay, so as you all know, there's diverse cosmological observations which all concur to suggest that the universe is dominated today by some mysterious dark energy that drives its accelerated expansion. And the microscopic nature of dark energy is of course unknown. What we do know is that if we think of it as some perfect fluid characterized by a pressure and an energy density, then it must have an equation of state which is less than -1/3 in order for it to be able to source the accelerated expansion in the Einstein's equations. And that must be compared. Maybe I can adjust the screen here so that you can see the full slide. Oh, how do I do that?
It's on the view, the top right. Yeah. The screen that's very bottom.
Oh, great. Oh,
And then minimize that one with a little.
and then I can move this.
Wait, before you put minimize it.
Oh, I don't like, oh. Oh. Okay. Okay. And so, and of course, that must be compared with, say, the equation of state for pressureless dust. W is equal to 0, or for radiation, W is equal to 1/3. And so, of course, as we were saying over lunch yesterday, you can think of dark energy also as a dark pressure. Yes.
You have it written as strictly less than.
Yes, that's right. It is strictly less than -1/3. So observations to date are perfectly consistent with the equation of states being of dark energy being -1. And so, in other words, it's a vacuum energy or cosmological constant. It's consistent with dark energy being a vacuum energy or cosmological constant. Although it's important to emphasize that other equations of state are consistent with the data, but one might consider vacuum energy or cosmological constant to be the simplest candidate and consistent with the data. It's in principle simple. If it were not for its size, of course, and the observed vacuum energy then would be this famous 10 to the -120 Planck mass to the 4th. Yeah.
When you put -1/3, how close can you get to -1/3?
Observationally, you mean?
Yes, observation.
Yeah, that's a good question that I actually don't know the answer to, because as far as I can tell, cosmologists, when they're constraining the equation of states, they're always kind of, because you have to kind of run the cosmology, the perturbation equations, initial conditions and then fit to the data, they're always putting in some kind of phenomenological ansatz for the equation of state, for example, this simple linear form. In that case, of course, it's you're very far from -1/3. But I'm actually, it's something that I'm thinking about these days, actually, how if you're taking kind of string motivated kind of scale field models and running the perturbations there, how far from W is -1/3 one can get it, considering that it would be time dependent, right? So there are constraints, for example, if you consider just a constant equation of state difference to -1, there's, bounds that are very far from -1/3, but when you consider that in reasonable models, it would change with time. I think there's probably more freedom than one tends to, play with, think about. Okay, so here we go. So, okay, on the one hand, that 10 to the -120 and 5 to the 4 is good, of course, because that is precisely inside this anthropically viable window. So if the cosmological constant were positive and much bigger than the observed value, then the accelerated expansion would be too big, and structures would not have time to form, so we wouldn't be here. And if the cosmological constant were negative and with magnitude much bigger than -120, then you would have had a big crunch a while before the structures could form, and we were here to observe it. So in that sense, we have to have, if there is a cosmological constant, it has to be within that window. And this actually indeed led to a prediction of dark energy by Stephen Weiberg back in '88. On the other hand, of course, this presents a big challenge to theoretical physics, because we know that the standard model contribution to the vacuum energy is around 10 to the 50 orders of magnitude too big. So this is the standard model contribution to the vacuum energy to around 10 to the 50 orders of magnitude too big. And so this, of course, leads us to the famous cosmological constant problem. So either we need some extremely fine-tuned cancellation against the standard model contribution to the vacuum energy, or an exact cancellation. Maybe that's going to be easier to explain with some kind of symmetry, and then an additional source on top of the vacuum energy to explain what is the dark energy. So this is, there are two parts to the cosmological constant problem then. Why is lambda so small and yet non-zero? And also it happens to be that this magnitude of the vacuum energy happens to be comparable to the matter energy density now. It didn't have to be like that, and so that is kind of the second part of the cosmological constant problem. Why is the vacuum energy comparable to the matter energy density now? Okay, so since this problem of the cosmological constant connected to dark energy occurs where, quantum physics and the vacuum energy meets gravity, one can hope that one might have a better understanding of it by considering quantum gravity, one of the leading candidates being string theory. So one can hope that a better understanding of string theory might lead us to some understanding of this problem. Okay, it's a big question, and we're far from an answer, but today I just want to give you a flavour of kind of the kind of things that we've been thinking about in the community, using some of my work as an example. And so the talk will kind of be split into two parts. So I'm first of all going to give you some overview of some idea of the work in looking for the vacua, so that's solutions to string theory which have a positive cosmological constant, and also alternatives to de Sitter under for dark energy, the main candidate in quintessence. And then in the second part of the talk, I'll discuss some kind of string-inspired alternatives for dark energy, which maybe will be easier to find some, which meet some of the challenges that we have to face when considering de Sitter vacua and quintessence. Okay, and it's important to emphasize that kind of as we're aiming at this theoretical understanding of what might be the microscopic nature of dark energy, that we're kind of looking ahead, that there are current and that there will be upcoming observations which are going to further constrain the dark energy, in particular its equational states. Okay. Okay, so as I think it's quite a broad audience, I want to kind of give the next couple of slides, just give a very big step back about the program of moduli stabilization and de Sitter vacua in string theory. So as you all know, quantum consistency implies that strings live in 10 space-time dimensions. We don't have a very, we're able to understand string theory only in very simple, fully, perturbatively, only in very simple backgrounds. If we want to connect to our universe, we have to go to more interesting backgrounds. And we can do that by considering two important expansions in string theory: the weak string coupling and the weak curvature or large volume expansions, the alpha prime expansions. And when we look at that weak coupling and weak curvature expansions, then we have an effective field theory description of string theory. In space-time, giving us essentially at low energies, we have 10 dimensions to the gravity. Of course, the 6 extra dimensions typically we expect to be compact and small to explain why we haven't observed them. And then at low energies below that compactification scale, below the prime scale, we expect to find a 4-dimensional effective field theory, where we have some 4-dimensional Einstein gravity, some supersymmetric standard model, and some hidden sectors, some dark sectors. Okay. So what's important for us is that in this 4-dimensional low energy effective field theory, the size of the extra dimensions, its shape, and the string coupling constant itself corresponds to scalar field in this low energy effective field theory. Those are the moduli. And the moduli, in the simplest compactifications, lowest order in these expansions of weak coupling and large volume, correspond to massive scalar fields, which can take any value. However, the value that they take determines not only the size of the extra dimensions, the shape of the extra dimensions, the string coupling constant itself, but also the masses and couplings of the standard model and the dark sectors and the vacuum energy. So a big problem kind of in string phenomenology, string cosmology, connecting string theory to the observed universe is the so-called moduli stabilization problem, finding mechanisms which give masses to the moduli and preferred vacuum expectation values.
Sorry, could I just pause you?
Oh, yeah.
If you wanted to move away from this small coupling, small curvature limit, could you put this on the lattice for simulating?
That's a very good question. This is, to my knowledge, not something that's been approached in string phenomenology. one way that people might try to meet the strong coupling regimes is via holography, but typically typically the efforts have been to find ways to stabilize the moduli that are consistent with weak coupling and large volume.
What's the question you're answering?
So Jasmine asked if we can go beyond the weak coupling limits by for example lattice computations. I don't know, lattice approach. Yeah. Okay, there you go. There's Susha's answer. Did you hear?
No, sorry, could you repeat
You
then?
said you don't have a theory to put on the lattice.
You're talking about some non-controllable combinations.
Yeah. Okay. So, okay, so right. So the problem we have to face is what is the physics that's going to kind of give a map to the moduli or and preferred vacuum expectation value for the moduli. And indeed, there are various string theory ingredients like higher dimensional fluxes, D-grains, Gaugino compensates, instantons. So both perturbative, well, classical perturbative, non-perturbative ingredients that one can include in a string compactification that induce a potential energy functional for the moduli. Always in this weak coupling large volume expansion. So just kind of very heuristically, you can think of what one can kind of compute this effective potential for the moduli. Remember, the moduli themselves are also correspond to the string coupling and the volume. And we understand this effective potential in expansion in the string coupling in the large volume. So, for example, if phi, we can think of phi as being the scalar field that corresponds to the inverse string coupling. So this is an expansion in the string coupling. Then we get to however, we have to face a very old problem, which is that if we understand this effective potential only in this weak coupling expansion, then with the weak coupling expansion, only the leading term is going to be important, and therefore you're really only ever going to be to get the runaway. In order for this potential to stabilize the string coupling, you'll need to balance different terms against each other, different terms in this expansion, the perturbative expansion, and then different terms in the expansion will have to be of the same order, comparable, and therefore you're only going to get stabilization at strong coupling, not at weak coupling, typically. The only way that one can get around that is if there's some kind of hierarchy in the coefficients of the expansion, and indeed that's possible. So there can be some topological choices that you make in the string compactification, which allow the moduli to be fixed at weak coupling and large volume, if it's a vacuum, so where the vacuum energy where the moduli stabilized is positive. Okay, and one thing that's nice, by the way, is that then having found having stabilized the volume at weak coupling and large volume, one can compute the potential energy at the minimum, and this will be a good approximation to the full vacuum energy, because any corrections, quantum corrections from will be kind of small, because we're exactly in the string loop and expansion. So corrections from the string loop and the higher string modes are suppressed. Though it's important to note that we're far from being able to fine tune the actual value of the vacuum energy to this 10 to the minus 120, because as soon as you to fine tune these things to 10 to the minus 120, then the higher order, the next leading order terms will be important. In any case, that's kind of the big picture setup. The idea is that there are enough kind of ingredients within these string compactifications that there's really a vast landscape of possible solutions, and those solutions will each have different vacuum energies. They can be finely spaced vacuum energies, so that the vacuum energy just becomes an environmental parameter, and we have our anthropic solution to the vacuum energy, which to the cosmological problem, and really that's the best so far today. Now, no matter how dissatisfying it might be, it is the solution that we have to the cosmological constant problem today. Yes.
The effective potential that I've got, is that just some cartoon of the kind of effect? Yeah.
Exactly, that's exactly a cartoon.
You don't get it from what's
No, what, yeah.
more challenge skills.
Yeah, that's true. This is a cartoon. This is a cartoon too, really, because obviously in an actual string compactification you have many moduli. It will typically be more complicated than that. Okay, this is a little bit less than a cartoon, but I don't want to get into the details of it, but just to show you the kind of things that are done. So this is kind of the low energy effective field theory of a particular type 2b flux compactification. The low energy effective field theory expressed in terms, it's an n equals 1 4-dimensional supergravity, so expressed in terms of the Kähler potential and the superpotential. It's just a particular choice of geometry, which is called the weakly warped deformed conifold. What's nice about that is that we know the metric for this deformed conifold. So typically, of course, we don't know the metric for analytically for Calabi-Yau. For compact Calabi-Yau is the non-compact Calabi-Yau, which then one can glue onto some compact Calabi-Yau, and one can work out the effective field theory for the key moduli, which would be the volume, the string coupling in this Z, which is the deformation modulus. One can compute leading alpha prime corrections, leading non-conservative corrections, and put everything together, and from all of that obtain a vacuum. So lift the moduli, give a potential energy function to the moduli and stabilize them it consistently with the weak coupling expansion and the large volume expansion over here, and with a positive vacuum energy, and all the kind of mass hierarchies that you need and stuff are there.
There are usually problems with string theory in decision vacuum. How is this overcome?
So, what problems do you mean?
usual statement is that the sitter is not, it's not possible to find the string solution to sitter.
Well, that's debatable. So there are many candidate solutions, scenario solutions to string theory that can have that corresponds to sitter vacua exactly by including various perturbative and non-perturbative effects in this way. So I kind of put here. So this is kind of in the class of models as the famous GLT and the large volume scenario. These are, however, intricate constructions. The question, well, and this is exactly, so then maybe let me go to the, so how much under control these are is under debate. So for example, we include D-branes, various D-branes there that might have back reactions that we haven't got under control. There are, well, let me say in a bit more detail here. It's actually the next slide. Okay. So in what I just showed you, I just considered kind of the leading alpha prime correction and a non-perturbative contribution, some instanton contribution. There are, however, several subleading corrections, sub-subleading corrections, which are known from various string loop corrections, high derivatives, back reaction of the sources, for example, the fluxes that you put to deform the conifold, and so on. And so one has to, then the question is, the reason why people, why that's still under debate is because we have to have under control the corrections and be sure that these sub-leading corrections do not spoil our solution. In principle, you could think it's fine because we ensure that the string coupling was stabilized at small string coupling and like the volumes are large, and so these corrections should be small. However, when one goes to compute those corrections, what one finds is that even though there are suppressions as expected, there are sub-leading corrections, so they're suppressed in the off-shell potential, they're suppressed in GS and large volume, but it turns out that those suppressions cancel in the VEVs of the moduli and in the VEV of the vacuum energy. So this is just, again, obviously you don't have to get the details, but just think of it as a picture. This is the vacuum expectation value of the potential, so the vacuum energy, the value of the potential energy at the minimum. And one can see that there are several terms that are actually not suppressed in GS or one over volume. There are some terms that are suppressed, but there are other terms that are not suppressed. And so in order for the solution that I just presented to you to actually be a solution, I don't have kind of the parametric suppression in GS, like I don't have suppression in small GM and large volume. I would have to compute these numerical coefficients and show that they're small in order for my de Sitter solution to be a genuine de Sitter solution. Right, so several corrections are not parametrically suppressed, by which I mean they're not suppressed in GS and large volume. Others actually can't be, there are others that you cannot simultaneously suppress in small GS and large volume. And so the consistent de Sitter vacuum means the topological choices to be made when you're doing a compactification such that these coefficients are small. Okay, and so indeed, this is where kind of the controversy lies. It would seem, though not everyone agrees with me, I should say, it seems difficult to get parametrically controlled metastable de Sitter vacua. It may still be possible to get kind of numerically controlled, so to find constructions where these coefficients are small, and then you have a genuine de Sitter vacuum. So that's, I mean, that's kind of the status of de Sitter vacua in string theory now. I mean, the constructions are getting more and more explicit, and the tests are getting more and more explicit and robust, and there's kind of a continual debate, and yeah, there isn't consensus yet, so we don't know whether or not there are de Sitter vacua in string theory, metastable de Sitter vacua string theory. It's but it's, I think it's, we can't, it's too early to say that there are not de Sitter vacua, that there are problems with de Sitter vacua. Yeah, and hopefully it's kind of, I guess what I want to communicate is that the constructions have to be rather sophisticated, and then that makes it difficult. Okay. So given the challenges in achieving a de Sitter vacuum, one naturally asked oneself, well, are there simpler alternatives? One thing that appears rather generically in string theory are kind of these runaway directions. It's quite easy to get de Sitter maxima. It's quite easy to, I mean, yeah, essentially you always get runaway directions at large volume and weak coupling. So can one hope to find some kind of scalar field which slowly rolls down the potential in such a way to generate dark energy in similar ways to inflation? One also has kind of axions. There are loads of axions in string constructions which have then periodic potentials. One can ask, can these axiom potentials be shallow enough to give you slow roll, or maybe you can fine tune initial conditions to sit on any of these hilltops. So a priori, it doesn't seem impossible to have some kind of quintessence as an alternative to a de Sitter vacuum. So that's quintessence, a slowly rolling ultralight scalar field. Of course, again, the vacuum energy, the potential energy needs to be around 10 to the minus 120 in factor of 4. And also now we have a scalar field that has to have a mass which is extremely light around the Hubble scale today, which is 10 to the minus 32 electron volts. So quintessence has to then face, even if we could find potentials that are able to sustain these slowly rolling ultralight scalar fields, we have to meet two fine-tuning problems now, not only the vacuum energy, not only that the cosmological constant, the vacuum energy has to be fine-tuned, but also the mass, which of course is also ultraviolet sensitive, has to be fine-tuned. And also if we have a very light scalar field, that will typically lead to fit forces which are unobserved, and string moduli, again, as I introduced at the beginning, they tend to correspond to masses and couplings of, for example, the Stanley model field. And so if they're rolling, that will lead to time variation of the fundamental constants.
So these corresponding issues you're they exist in any quintessence. It doesn't have to be a string.
Yeah, that's true. Yeah. So this is, sorry, this is actually about any quintessence. And then indeed, so the fine-tuning, if it forces is true for any quintessence, the fact that the scalar field only corresponds to two fundamental constants, like this quote, quite stringy. Okay, so string axions, over here, or some modulus that corresponds not to the string coupling constant or the bulk volume, but some kind of shape modulus, like the size of some local cycle inside the Calabi-Yau, for example, so some local modulus which might be kind of geometrically separated from wherever the standard model is in the extra dimensions. These could ameliorate the fifth force problem and the time variation of the fundamental constants. However, it's actually, even though it's very easy to get potentials like this out of string theory, in string theory, these potentials are essentially always too steep to sustain kind of to source a slow roll that's necessary for quintessence. So you either then need to start playing with kind of all the different ingredients to make some fine tuning of different ingredients to make the potential shallow enough to sustain slow roll in similar way to what we had to again we had to play to find the sitter vacua, or you can potentially hope to fine tune initial conditions so that you happen to be sitting at some unstable de Sitter maximum. But so you typically, if you do manage to do some fine tuning to get a shallow potential, you typically need super Planckian field distances, super Planckian axion decay constants. Those then lead to kind of a loss of control. You expect higher order corrections to become important in the effective field theory. So in the end, the string constructions for quintessence, they in the end have similar ingredients and challenges to de Sitter constructions and really even more when you throw in the fifth forces and time variation, fundamental constants, and so on. And so kind of these swampland expectations that perhaps there's issues with de Sitter vacua, quintessence doesn't tend to fare any better somehow. So there, for example, swampland constraints that imply that the axion decay constants must always be sub-Planckian, which makes it difficult to get quintessence from axions and so on. Okay, so that's kind of the status of kind of de Sitter vacua and vanilla quintessence models in string theory. And now in the last 10 minutes, is that clock's right?
Yes, pretty much.
Yeah, okay. So next 10 minutes, I'll give you some flavor into the string-inspired scenarios, which meet some of the challenges that one faces when trying to get vanilla quintessence from string theory. The elephant in the room here is the cosmological constant problem. So here in this next part of the talk, I'm just going to assume that there's some solution to the cosmological constant problem, which sets the cosmological constant to 0, and then we'll be introducing something on top of that to explain dark energy. So something else cancels the contributions to the vacuum energy from the standard model. Okay, so although the state of the metastable de Sitter vacua is unknown so far, we do, as I showed you, unstable de Sitter vacua certainly exists in string theory, and we believe in nature. So, for example, just think about the Higgs. So the Higgs we have our Mexican hat potential. At high temperatures, the unstable de Sitter vacuum here, of course, it turns into a metastable one with the symmetry restoration. So even in nature, we think we have a metastable de Sitter. In the case of the Higgs, this metastable de Sitter, of course, did not lead to an accelerated expansion because the potential energy was dominated by the radiation energy density at high temperatures. What we propose is to consider some kind of light hidden sector where there are some kind of dynamical effects which can generate a metastable de Sitter that does dominate, whose vacuum energy does dominate the universe and drive an accelerated expansion. So let me show you in a bit more detail what I mean. So I'm going to take a very simple model now. So just two interacting dark scalar fields, phi and psi, with canonical kinetic terms and a potential energy functions which takes this form. Phi, which will play the role of my dark energy field, I'll assume it has either a hilltop potential, like the Mexican hat potential, or just an exponential runaway. And psi, will either play the role of dark matter, a dark radiation, or even kind of some subdominant quintessence field. It has a mass, and what's key to the scenario is that there's an interaction term between our two scalar fields, which goes like this. So lambda is kind of a parameter which gives like the field range of phi somewhere below n Planck, and then the quartic coupling is parameterized by this max parameter and interaction over lambda. Okay, so in this kind of simple Tory model, either phi or psi alone, so with this hilltop potential or just a massive scalar field psi, they can source slowly rolling quintessence, but only if you fine-tune the initial conditions to be at the hilltop, or you kind of ask that the fields have super-Planck field distances. Okay, the fine-tuning is not very attractive. Large field distances tend to lead to a loss of control. But now what I'll argue is that just with this interaction term, and psi behaving as dark matter, dark radiation, or some dominant dark energy field, that can psi, and with the interaction term, can stabilize phi in such a way that this runaway phi, otherwise runaway phi or Mexican hat phi, can have some transient de Sitter vacuum.
So these dark scalars in no way interact with the standard model.
Exactly.
And do they require any vacuum exploitation value?
So I will show you now. So everything, of course, has to interact gravitationally with the thermal, and so that will lead to constraints. But let's assume that the interactions are weaker than that can be made weaker than gravitation with some kind of sequestering, some geometric sequestration. Okay, so
Sorry,
yeah.
could I just interrupt? Is there any reason why you didn't have any mass mixing term for phi and psi?
Why didn't I have any what?
Mass mixing term for phi and psi.
So you mean you mean okay, just a phi psi. Yeah, oh gosh, sorry, and now I'm trying to remember what the, can I come back to that? Yeah, so
Yeah, of course.
it may indeed, I think I think it would alter the dynamics, and so I might have to assume some kind of Z2 symmetry or something to not have that term. Right, so this is going to be simpler. The analysis is going to be simpler if I don't have that term, which I can hope to have by imposing some kind of symmetry.
Okay,
Yeah.
thank you.
Okay, very good. That's a good question. Yeah.
The hilltop potential for phi.
Yeah.
I mean, you're essentially assuming a bit of.
Yeah, that's very true. That's very true. That's my own opinion. So I've just chosen the quantum potential to have. Yeah. It might. Yeah, I seem to remember that. So I think depending on the scales and stuff. What I mean, because the interesting stuff is happening at the hilltop rather than that -1. So yeah. Okay, so I'm going to just because I don't have. Oh, okay, I've essentially run out of time, so I'll just tell you the main idea for when in the case when psi behaves as matter. So when psi is some dark matter. Okay, and let me just to begin with, I'll just assume some freedom of some water background. Assume that the energy density is dominated by the potential energy of phi. Assume that the mass, that the dynamics of psi is dominated by the mass, by its mass rather than by the interaction term, just to simplify things. Then the equation of motion for psi is just the Klein-Gordon equation. Because I've run out of time, so I think I'm just going to skip to the next slide and just explain. Oh, really? Okay, that's lovely. Okay, so then I'll try and. So okay, so we're going to assume some initial conditions which are not tuned in any way, just asking that psi starts. Just assume that psi starts away from its minimum of its m squared psi squared potential. Assume that the mass of psi is bigger than the Hubble constant today. So the solution to the Klein-Gordon equation is known as well-known oscillations in its potential. It's just oscillating the quadratic potential with the amplitude of the oscillations decaying with time because of the Hubble friction. So one can consider this to be kind of a collection of scalar particles oscillating coherently with the frequency going as the mass. Now let's consider the impact of this psi, this background of coherently oscillating scalar, in the dynamics of phi. So we have this quartic interaction, and there's an effective mass contribution for phi from the background in psi, right? So this is then an effective mass for phi. This is the mass, the tachyonic mass from the unstable distance, and there's a positive contribution decaying with time from the background in psi. So considering the case of the hilltop, phi can the potential for phi, the effective potential, can have transiently just its minimum, that what was the maximum becomes the minimum, where it can then source dark energy. So psi's amplitude is decaying because of the Hubble friction, and eventually that the positive contribution to the mass here becomes insufficient, so that the minimum becomes a maximum again, and you can get estimates for the number of p-folds of accelerated expansion that depend on the parameters in this way. the story is a little bit more complicated than that because it's not just, we're not, so you, to get this estimate, you're kind of averaging over the choose of psi. Really, psi is oscillating to their time even when it's passing through zero, and the minimum of psi becomes the maximum. So one needs that the time that psi spends in this instability region to be less than the time scale on which phi will roll. That gives another estimate for another rolls. And then one can do a little bit better actually, and one can kind of translate the equation for psi, the dynamical equation for psi, in terms of the mature equation in this way. So this is the mature equation, so it's just a second order differential equation with a periodic stiffness function, whose solutions are well known. And what one sees is that there can be kind of this parametric resonance instability, which is kind of analogous to what happens in preheating. So you can see that if the mass of psi is too big, then there's this instability in phi, and the dark energy combination ends too quickly. But so long as the mass is less than of psi is less than around 15 H0, then you're safe from the parametric instability. That means that so the mass of psi ends up having to be quite light, right? It's not quintessence light, which is less than H0, but it's still pretty light, less than 15 H0.
This is the result from the picture you got yourself.
Say again?
Yeah, this is what I can see the reference up there. Yeah.
Yeah.
Yeah, I was just saying maybe instead of parametric resonance, you could call it Parameswaran.
Okay. So the fact that the mass of our dark matter field has to be really that light means that actually the psi cannot play the role of, well, it means it starts behaving like matter and oscillating after radiation matter quality. So it can't be all the dark matter, it has to be some kind of subdominant component of the dark matter. And then one can actually, so that was just kind of assuming, focusing on the dynamics of phi and psi. We can also put in the psi model, we call dark matter, and solve the full cosmology numerically and sorry, it's not very visible. So this is kind of the numerical solutions for phi is the blue line and psi is the yellow one. And essentially what's happening is, so we start off with both fields sitting somewhere away from their minimum. And in fact, what's nice is that you don't have to fine tune the initial conditions. At some point, so they start off frozen by the Hubble friction, then at some point phi starts rolling in its potential, with its amplitudes of course decreasing because of the Hubble friction, always giving some contribution to dark energy because of its potential energy. And then at some point psi starts rolling as well, and then you have this kind of nice dynamics from the mature equation, and phi essentially becomes kind of locked in this dark energy, transient dark energy epoch, until finally the amplitudes of psi oscillations become so low that phi will start rolling to its true minimum, which I choose to be at 0. Anyway. Okay, and one can match the lambda CDM dynamics up to today and a bit beyond. Yeah.
May I ask a question? So you say that psi cannot be all of your content. I don't remember you introducing an explicit mass term for phi. Is that correct?
Yeah, so I assumed either just a runaway potential, so it doesn't have a mass term, or this Mexican hat. So there is this, so around phi equal to 0, there's essentially tachyonic mass.
Yeah. But you are reducing the parametric resonance?
Well, actually, I'm choosing my parameter space so that I avoid the parametric resonance, because the parametric resonance actually takes me out of the dark. You've got too quickly.
Well, I mean, there are also benefits to parametric resonance.
Yeah.
Like,
But this is kind of, so there's the amount, I mean, the equations are the same, but in inflation, it's like the inflaton field that's sourcing the instability.
Yeah.
Here, it's the dark matter field that's sourcing the instability in the dark energy field. So the equations are the same, but the physics is a bit different. Okay, so I think okay, so I'll just I'll just point out that one can constrain the parameter space with various kind of theoretical limits and observational limits. For example, that there's not too much energy density in this light dark matter field, that you get enough E-folds of dark energy, and so on. And I'll note that one can play the same game with both. I've showed you I showed you the case for the hilltop potential. One thing that's very nice is that one can play the same game for the runaway potential. So it's kind of a dynamical mechanism of core moduli stabilization, which is quite nice. And there's parameter space available where psi behaves not as dark matter, but as dark radiation, or as some subdominant dark energy. And what the key is that kind of one of the interesting things that kind of make it potentially easier to, well, potentially nicer. The test in string theory is that you don't need to fine-tune initial conditions, and you don't need super Planckian field distances. Yeah, okay. So then I'll just summarize what I wanted to say. So the existence or not of metastable descriptive vacuum, it's still an open question, but I think it's fair to say that the constructions are becoming more and more explicit, and so are the tests of their robustness, and there's kind of a fruitful debate going on there. Okay, and then I want to make this point: interacting dark sectors perhaps make it easier to find de Sitter vacua, transient de Sitter vacua. Well, one has to, of course, see whether or not this idea can be embedded in the string constructions. But this transient de Sitter vacua can potentially be sourced by coherently oscillating dark matter, finite temperature effects from dark radiation in much the same way as the Higgs potential, but with the parameter space that the potential energy dominates over the dark radiation. Or some sub-Planckian cellular incandescence, and as I said, the runaway moduli. So it's nice that one can have this kind of natural cosmological history without fine-tuning of the initial conditions, or super Planckian field distances, and also near transient de Sitter epoch. And it looks like the effective field theories that we need, they're consistent with the so-called Twomtime conjectures that people have been proposing. For example, which propose that metastable de Sitter are not embeddable in an easy complete theory or string theory. I just mentioned that absolutely, because you have this quartic interaction, that can lead to some UV sensitivity to the matters of both psi and phi, but actually didn't if you check, it doesn't require, you don't have to ask much of the UV cutoff, just be a little bit lower than lambda, which is just a little bit lower than Planck. You can avoid also just understand relative forces, time variation, fundamental constants, but that's going to need some kind of model rolled in some geometrical sequestering for the dark sectors, between the dark sectors and the visible sector, and of course, it would be important to explore whether or not it's viable within string theory interacting dark sectors, and if they're potentially observation probes for Which there.
Nothing really wrong with time variation of pattern. Is there?
Well,
The
yeah.
web changes across the whole.
yeah, this is very true. No, that's you're probably right, that there's a lot of degeneracy again in the cosmological, when we're fitting all the cosmological parameters, maybe there is some freedom there as well that would, oh, that's a fair point, yeah, it's true. We tend to just say it as a, as a problem, but considering all the degeneracy in the cosmological data, there's probably room for it. Yeah. Yeah, good point.
Reduce the anthropic.
Yeah.
Back when you were talking about the parametric resonance, so phi in itself doesn't contribute to dark matter. Is that right?
That's right. Phi plays a role of, yeah, of the dark energy field.
Yeah. Yeah, so what I was thinking about with the parametric resonance of psi was that usually when you have a, let's say, dark matter that is very light, you have to worry about it being relativistic and the lots of constraints that you have to worry about. Whereas if you produce it through parametric resonance, it never thermalizes with the sample of that. And you know, it's a whole other scenario rather than even freezing. So your dark matter could be as light as you want it to be, and you're perfectly safe from
Yeah. Yeah. But yeah, that's it's interesting. I my feeling is that it will still if I'm kind of using the parametric resonance to kind of produce the dark matter, the parametric resonance from phi to produce dark matter, then phi would not be playing a role of dark energy at that point. So you kind of yeah.
And you did mention at the end that it would be interesting to see if there are observational proofs of it.
Yeah.
That's not something that.
Yeah, I mean, in some sense, you know, there is the already kind of some constraints from observations on the parameter space. So, for example, the constraints from the light dark matter, as you mentioned. But no, one thing that we're kind of one nice possibility probably would be if there, I mean, string theory of course has potentially many hidden sectors with many mass ranges kind of involved. So it would be interesting if there was some early dark energy from some similar mechanism, because then there would be the exits from that early dark energy which might leave some signatures, or even the early dark energy itself, to help with various dimensions. So for example, when the psi is behaving as dark radiation, then there can be kind of first order phase transitions and potentially gravitational waves and stuff. But in a sense, we kind of, chosen parameter space that we're exactly recovering lambda CDM up until today, and then so, but there still might be, if we go to, that's just the background evolution, if we go to perturbations, maybe there's.
It's not really practice, it's not really research, but that's just one in case you happen to know. So does low quantum web cosmology have a proposal for resolution of that?
Yeah, gosh, I probably should know that, and I don't, sorry.
Sorry.
Yeah. Yeah, no, I really know. I imagine people have had this debate.
Suspect the answer is almost certainly yes. People go along to this matter.
Yeah. Yeah. Yeah, I mean, yeah, I think it probably really is true that the anthropic principle is so far both the best, but also the worst, right, solution. I don't think I think there's gonna be some better solution to the cognitive results of that will help us understand what that can do as well.
You
We
mentioned
haven't got there yet.
the whiteboard kind of prediction.
Yeah.
Can you explain how that works? Because I didn't really understand it.
Well, it was really just that. So it's really just if he noticed that if the dark energy if the vacuum energy is big to positive and bigger than this value, then there's too much accelerated expansion and structures don't form. If it's negative and with a magnitude bigger, then you get to a big crunch before structures form. And oh, why did he not? Yeah, no, that's true. Yeah, I'm sorry. You're right that lambda is equal to 0 is anthropically viable. But if you, yeah, no, but well,
It's not so big. You're saying a prediction.
yeah, gosh, it's that's been in my slides for many years. My prediction is that in that 88 paper, I suppose, yeah, why did he not just say rho is equal to 0? I actually don't.
No, I think that's fine. That's
Yeah.
perfectly fine.
Yeah.
I'm just wondering why it predicts that energy.
Well, I
It
think,
predicts-
yeah,
It says 0 is perfectly consistent.
no, yeah, no, you're absolutely right, the 0 is consistent. I suppose the point,
It's a constraint that is not at all I can see it.
yeah, no, that's,
I thought my better position was, unless there's some reason why it should be 0,
yeah,
it's not. There's no solution to say that.
Yes,
It's not, you're not gonna
The usual argument at the time would be that if it is so close to 0, it's minus between something, a small number of minus 10 to the minus 1 to 3 and plus to the minus 3, it must be 0.
well, I mean, because in that paper, he's going through, in that paper, it's just, it's like a review, essentially, if I remember right, and he goes through the different, different symmetry principles that might help, like, including the conformal symmetry. And the point is, of course, always that either the symmetry is broken, the symmetries usually lead to new particles, right? New light particles, and which are not observed. And then if you want it to, then you need it to be broken to explain why you don't observe the new light particles, and but then breaking it in a way that evades the new light particles means that it has. The scale of that kind of deal again. Yeah. Yeah, no, you're right. I have to go. Yeah, no. Yeah. I'll have to. I have to go back and think of that. Sorry.
Fred Bogner was in it.
Well, no, that would Frederick almost look at this thing. Now they are
All the smaller is the student with 0.
Yes, it would be, yeah, but
You have to be.
if at the time in 88, if anyone said,
Yes.
this number here, the tribute was, what is your prediction what it is?
Well, that's why for you, I guess.
Well, if you're saying between, that's exactly what I'm saying, between bounds which are very close to 0, you would.
Tell me how you would find it, because I want to natural and apply it, it's not so good.
Uh-huh. Yeah.
Someone who wasn't in Spain was more. I don't like science was more.
Was there any questions online?
Oh, yeah, sorry. Oh, I think it was just Jasmine saying goodbye. Yeah.
Okay, thank you.
Thank you, everyone.
Thank you very much.